grand challenges for engineering designed to improve the quality of life. One of those challenges is engineering better medicines. Part of developing better medicines is improving drug delivery systems through controlled release. Controlled release delivery systems differ from normal, widely used, immediate release medicines by releasing a drug over an extended period at a predictable and programmed rate. It allows for the targeting of specific areas in the body, optimization of therapeutic effects, and more infrequent dosing. pH-dependent or pH-responsive capsules are a form of controlled release delivery, which release according to changes in pH environment. They are normally designed with a coating built to withstand the stomach's acidity, so that they may be used to dissolve in areas such as the small intestine for site-specific delivery.
Many high school students are briefly introduced to these topics in their curriculums, but are met with minimal supplemental materials when they dive deeper.
We were tasked with creating a museum exhibit that educates high school students on the grand challenge of engineering better medicines. We choose to approach this by focusing on pH-dependent or pH-responsive capsules.
The exhibit has a few specifications to adhere to, including the use of a microcontroller, a budget of $150 overall and $50 for new material, and showcasing 3 disciplines through the William States Lee College of Engineering. There must also be at least 1 engineering technology and 1 engineering discipline.
We designed an exhibit that is similar to a marble track. It allows students to compare how regular pills dissolve compared to pH-dependent pills using 2 different sized marbles.
In generating our design concept, we started by analyzing controlled release, current technology, and relating existing educational materials for high school students.
These often lacked interactivity or student prior knowledge. We designed a marble track that represents the digestive system so students can see the difference between regular pills and controlled release pills.
When beginning the construction of our design, we started off with an open marble track and a secondary exhibit which allowed users to utilize a slider mechanism for a pop-up display. We received a peer review that suggested our design be shaped like a mannequin, so we incorporated that into our next schematic.
We also decided to eliminate the secondary exhibit to give more time and resources to the marble track. For our first prototype, we put the tubing into the mannequin in a sequential row configuration.
While one part of the team worked on the physical prototype, another part of the team developed the code for programming the Arduino, motion sensor, and LED light using C++ and Tinkercad. We tested the code and physical components multiple times before attaching them to the design.
We realized our previous configuration of the tubing was causing the marbles to become stuck in the turns, so we experimented with a spiral configuration, which led to our final design.
Beginning to test our exhibit, we realized we need to create a way to stop the larger pill from entering the small intestine, so we glued part of a popsicle stick to the inside of the stomach as a choke point. We also experienced issues with the marbles falling out of the stomach, or not following a path to the second hole, so we created a path and shield with popsicle sticks.
We tested our final design product by running the 2 marbles we created through the tubing. We first tested the larger pill, which was designed to represent traditional delivery. The pill traveled through the esophagus tube and stopped in the stomach.
Next, we tested the smaller marble, which represented the pH-dependent delivery. This pill traveled through the esophagus, into the stomach, and through the spiral of the small intestine. It set off the PIR sensor, which turned on an LED meant to represent dissolution.
Our potential customers include high school students throughout America. There are about 17.3 million of them. We can also target our design towards the thousands of high school schools around the nation. Our design is also easily expandable due to its simplicity and affordability.
It also provides a low-cost approach to an educational resource at an overall cost of only $43.26. Throughout this project, we gained new knowledge and skills in a variety of areas. We learned how to use a decision matrix to weigh potential designs and how to write technical documents such as a design report. We also gained some experiences in the C++ coding language after using it to code our Arduino, as well as public speaking, where we would provide presentations to peers on our prototype and design.
If we had the opportunity to redo this project, we would have started with the mannequin rather than incorporating it later into the design. We also have utilized a different motion sensor, like an IR sensor, to minimize errors.
Overall, our exhibit simulates how regular acting pills dissolve in the stomach, while pH-dependent pills are designed to withstand certain pH environments to target different areas of the body or produce longer-lasting effects. Our PIR motion sensor picked up on the marbles most times, but did have some inconsistencies. Our next steps would be to replace the sensor with a different type and add other digestive organs. We would also add a recollection chamber at the bottom of the exhibit to hold the pills for visitors to use.